Hello, welcome back. So, in this module we are going to look at addition and subtraction in 1's complement and 2's complement form. So, before we go into the actual mechanics of 1's complement and 2's complement, I want you to go back and look at this number circle. So, let us assume that these numbers as before were only, so these are 4-bit values, right. Let me just assume that we are looking at unsigned interpretation of those. So, this will be number 0, this will be number 15, this is number 11, this is number 3 and so on, right. Let us keep it as it is. Now, if I ask you to do addition, right, let us say I ask you to add 3 to 5, right. I want you to add number 3 to number 5. So, in the number circle you can do something very interesting. You start with the number representation for 5. So, what is the representation for 5? It is 0 1 0 1, right. If you know that, and if you have to add 3, you go 3 steps forward, 1 2 3, that is the number, that is, so this 1 0 0 0 is the binary representation for 5 plus 3, we know that it is 8. Let us take another example. Let us say I want to do 7 plus 6, right. So, I need to start with the binary representation for 7. This is an unsigned circle. So, I start with the binary representation which is 7, 0 1 1 1. I go 6 steps forward from here, 1 2 3 4 5 6, 1 1 0 1. So, 1 1 0 1 actually stands for number 13, we know that, right. So, this is a good thing. In the number circle, if I start from a number and I take so many steps forward, I will end up with some other position in the number circle, and that number circle gives me the representation for the result that I am looking for. There are a few problems, however. For example, let us say I ask you for 14 plus 2, then you would start from 14, which is 1 1 1 0, and you go 2 steps forward, you end up with 0 0 0 0. So, if you say that 14 plus 2 is 0 0 0 0, it is technically not correct. 14 plus 2 in decimal is 16. However, since I am forcing you to give only a 4-bit representation, even in the unsigned numbers you cannot represent 16 using only 4 bits. So, this is the first wake up call that you should all have, that in any representation, if you restrict the number of bits, you will not be able to represent all the numbers, which means addition and subtraction and whatever you do may result in something which is not correct. So, the result that you get may not be correct, because you are adding numbers which are exceeding the range in which things can be represented. So, I want to do something else. So, I want to do something like this. Let us say I want to do number 14 minus number let us say 5. I want to do subtraction. So, if I want to do subtraction, one thing you can do is you can start from here 14 and go 5 steps in the counterclockwise direction. So, you start from 14, go 5 steps backward, 1 2 3 4 5, that is 1 0 0 1. So, 14 minus 5 is 1 0 0 1 or 9, so which is correct. So, let me try another example. Let us say I do 5 minus 4, then 5 is 0 1 0 1. If I go 4 steps backward, 1 2 3 4, the result is 1. So, we are good. This just like addition, we can end up with small problems. So, for example, if I start with number 2 and I subtract 5 from it, I start with 2 and then I have to go 5 steps backward, 1 2 3 4 5, right. So, it looks like 2 minus 5 is minus 13, right. 1 1 0 1 is 13. So, 2 minus 5, it actually gives plus 13 as the result, not minus 13. So, in the unsigned representation, you cannot even represent negative numbers. So, 2 minus 5 may end up with 13. So, this is something that is wrong, but given that we can represent only using so many, we cannot represent negative numbers, we cannot do anything about it at all. So, no negative numbers can be represented. So, just keep this in mind, because we will need this kind of interpretation for the other ones also. So, now let us jump forward. If I want to do addition and subtraction of signed numbers, when I say signed, it could be signed magnitude, 1's complement, 2's complement, it could be any of those, right. We will have to come up with some idea for adding the signed numbers first. So, addition and subtraction are two different operations, right. So, we need to come up with an idea for adding numbers, but subtraction becomes slightly easy. what you have to do is subtraction is usually performed as 2 steps. So, if I want to do something like this, let us say I want to subtract y from x, then I can as well do this. I can do it as x plus minus of y. So, as long as I take y, which is a positive number, which is some number. So, I have x and y are 2 different numbers. If I take y and negate it, and if I add the negated result to x, that is equivalent to doing x minus y. So, that is the first thing that I want you to note. So, if I want to subtract number y, it could be positive or negative from number x, which could again be positive or negative. All you have to do is take y, negate it, add it to x. So, this is a key thing that we will do over and over for all the representations later. So, let us start with the very first signed representation, namely the sign magnitude representation. Addition and subtraction in sign magnitude representation, negation is actually trivial, right. So, if you want to negate a number, all you have to do is take the most significant bit and flip it. So, if it is positive, it will go to negative, if it is negative, it will go to positive, that is okay. However, addition is relatively complex. Because addition is complex, subtraction also becomes complex, because subtraction is negation followed by addition, right. So, addition is complex because sign bits and relative magnitudes must be compared to perform the overall operation. If I give you something like add 011 with 010, then the result can actually be a problem. If you end up with 100, and if you leave it as it is, it is saying that 3 plus 2 is not 5, but it is telling you that the number is 100, which is negative 0. So, this is okay, this is a minor problem. The more complicated problem is if I give you numbers like plus 5 and minus 3, you want to add them and so on, it is not easy to do this using the sign representation. So, this is the reason why sign magnitude representation is not useful in computers. This was the first representation that people came up with, and later they realized that it is not really nice because addition becomes a very complicated process. So, let us see how to do addition in ones complement representation. Addition itself is done in 2 steps. First one is you add all the bits, right. So, if I are given 2 numbers which are already in ones complement form, so that is the key thing, right. When we say addition in ones complement representation, the 2 numbers are given in ones complement form, the result is expected in ones complement form. The question is how do we do it, right. So, we know what the input and output requirements are, but we do not know how to do it, right. So, I am explaining you the process of how to do it. If I want to add 2 ones complement numbers, it by itself is done in 2 steps. So, the first step is you add the bits as it is, you treat the numbers as though they are unsigned numbers and do the addition as it is. So, we will talk about how to do unsigned addition later, but this is also something that I have given you as a homework. I told you to add 2 4-bit numbers by designing half adder, full adder and 4-bit adder, right. You have already done that. So, to add two numbers in the unsigned form, it is relatively easy. What you are going to do for ones complement is treat the numbers as though they are unsigned, do addition first. So, add all the bits, carry out of bit position I must be added into the bit position I plus 1. This is just like regular decimal. If I add 2 digits at the 100th position, the carry that is coming out will go to the 1000th position and so on. It is the same thing. The key thing is add the result of the first step, which means the leftmost one, with the carry out of the MSB position from step 1. So, this is called end around carry. So, I will show you an example of what this means and it will make it clear to you. So, let us look at let us say 1111, right. If I want to take 1111, 1111 in the ones complement representation is number 0, this is actually negative 0, and if I want to add 0010, which is 2, then the way to add that is you add ignoring the fact that they are ones complement numbers, just add them as it is. So, 1 plus 0 is 1, 1 plus 1 is 0 carry over 1, 1 plus 1 is 0 carry over 1, 1 plus 1 is 0 carry over 1. The end stage carry, you take it and add it as the last at the last position, right, at this rightmost position. You add it once more, and when you do that, you get this result. If this results in carry now, do not do anything, right. So, for ones add the numbers, if there is a carry, take that carry and add it once more, and whatever result you get in the n digits, n bits is your final result. If the second addition gives you another bit, ignore it, do not do anything with it. So, this is what the ones complement addition is. If you want to do ones complement subtraction, in this case this 0 0 0 is negative 0 and we want to subtract 3. So, 0 0 1 1 is 3, we want to subtract 3 from 0, we know that the result is minus 3. Let us see how to do that. So, if we are doing subtraction, the first thing we do is whatever this is, right, we keep it as it is, and I said minus of a number, we will treat it as though it is, so this is negation of a positive number. So, this is x minus y, we will treat it as x plus minus y, and how do you get minus 3? Minus 3 is just flip all the bits of plus 3. So, it is 1 1 0 0, again you add it as before, in this case the end carry is 0, you add the end carry, the result is 1 1 0 0, 1 1 0 0, if you go back and interpret it in ones complement form, it is negative 3. I want you to quickly do that before we go to the next slide. So, 1 1 0 0, I want you to convince yourself that it is minus 3. The way to do that is note down the most significant bit, if it is 1, the result is negative, so it is negative, flip all the bits, right. So, flip all the bits 0 0 1 1, 0 0 1 1 interpreted in unsigned form as 3, so it is negative 3. Just convince yourself that this is the case. Subtraction in ones complement is you first go and negate because it is trivial to do, and then you perform the addition as I showed earlier. So, it is a fairly straightforward process. So, let us see several examples of ones complement addition. So, let us say I want to do this, I want to add positive 5 with positive 2, I know that the result must be positive 7, and in all these cases I am going to assume that the numbers are represented using 4 bits. So, how do you represent plus 5 in 4 bits in ones complement? It is 0 1 0 1. So, plus 5, the tightest representation requires 3 bits, it is 1 0 1, but I said we will do all the operations in 4 bits. So, the sign is 0 1 0 1. So, 0 1 0 1 is the ones complement interpretation would give you plus 5. How do you represent plus 2? It is 0 0 1 0, right, and I want you to add this. So, now we will forget the fact that we are actually adding ones complement numbers, we will directly add them as though they are unsigned numbers. When you add them, the unsigned numbers give you 0 1 1 and the carry out that is given is 0. So, there is nothing further to add, the result is 0 1 1 1 itself. So, if you take 0 1 1 1, interpret that in the ones complement form, you will see that it is plus 7 itself. Let us do this next set, minus 5 added to plus 2. So, how do you represent minus 5? So, for minus 5 you should take the representation. So, let me do that on a piece of paper, right. Minus 5, if I want to write that in if I want to represent minus 5 as a ones complement number, I first take 5 which is 0 1 0 1 and I flip all the bits around. So, that is 1 0 1 0. So, 1 0 1 0 is actually minus 5 in ones complement form, right. So, we have that and I want to add plus 2 to it. So, plus 2 is 0 0 1 0. So, minus 5 is 1 0 1 0 and plus 2 is 0 0 1 0. I add both of these, it results in 1 1 0 0. So, for this 1 1 0 0, I want you to remember that 1 1 0 0 is not generated any carry. So, because I added 1 and 0 which is a 1, it did not generate any carry, nothing else to do. If you go and interpret that, you will see that it is minus 3. Let us look at this one, 5 plus minus 2, right. So, this 5 plus minus 2, we know that it should be plus 3. Let us see how this will work. Plus 5 is 0 1 0 1 and minus 2, so 2 is 0 0 1 0. So, minus 2 should be 1 1 0 1, you add these two now. When we add these two, we are generating some carry outside. We take this carry, add it to this and that will result in 0 0 1 1. So, we are taking this carry, it is as good as removing it and adding it to the last stage, and you put this together, it is 0 0 1 1. So, we know that plus 5 added to minus 2 is plus 3. So, we are still doing addition here, and if you want to do minus 5 plus minus 2, minus 5 is 1 0 1 0, we have done this here, minus 5 is 1 0 1 0 and minus 2 is 1 1 0 1. We add these two together, and this case also generates a carry, in this case it is generating a 1, and you add the 1, that gives you 1 0 0 0, and we know that 1 0 0 0 interpreted in 1's complement form is negative 7. So, this is the result of 1's complement addition. Let us do addition in 2's complement representation before we go to subtraction. So, addition is performed by adding all the bits as though they are unsigned numbers. Any carry out from one position should go to the next position, and the last stage carry can be ignored completely. So, in the 1's complement we took the last stage carry and we added it back. In 2's complement, when you add two numbers, the last stage carry, you do not have to do anything with it. So, let us look at an example. So, if I take 1 1 1 1 and I add 0 0 1 0 to it. So, let us forget what the values are for a while. If I tell you that this is 2's complement and this is 2's complement, I want you to add, you just add these as it is. This generates a carry 1, you ignore it, take only the last 4 digits and you put that as the result. Let us see whether this is correct first of all. 1 1 1 1 is minus 1 and 0 0 1 0 is 2 in the 2's complement representation. The result seems to be 0 0 0 1. If you interpret that in 2's complement, the result is 1. So, it is consistent. If I want to do subtraction, so in this case we are subtracting plus 3 from 0, right, we want the result to be minus 3. So, to do that you take 0, right, 0, this is subtrahend and this is minuend, right. Subtrahend you keep it as it is. So, subtrahend is what you are subtracting from and minuend is what you are subtracting. So, if I do a minus b, a is the subtrahend and b is the minuend. So, subtrahend we keep it as it is, and for the minuend, so we are doing minus b, right, minus b is the same as plus of minus b, right. So, we take this which is 0 0 1 1, I know that number interpreted in 2's complement is 3, I go and look at the 2's complement representation of minus 3, that seems to be 1 1 0 1, you add these two together and the result is 0 1 1 0 1, again you ignore the carry and that gives you 1 1 0 1. So, this result is minus 3. Let us see more examples here, there are several examples. So, let us look at plus 5 and plus 2. So, plus 5 is 0 1 0 1, plus 2 is 0 0 1 0, I add these together it is plus 7. So, that is straightforward. Minus 5 is 1 0 1 1 in 2's complement. So, this is slightly different from 1's complement. So, it is this is 1's complement plus 1 more. So, in 1's complement it should have been 1 0 1 0, in 2's complement minus 5 is 1 0 1 1. So, you take 1 0 1 1 plus 2 is 0 0 1 0, you add these two together, the result is 1 1 0 1. There is a carry that is 0 that is generated, we ignore it anyway, whether it is 0 or 1 we ignore it. If you want to do 5 and 5 plus minus 2, so this is not subtraction of 2 from 5, we are adding minus 2 to 5. So, plus 5 is 0 1 0 1, minus 2 is 1 1 1 0, you add these two together, there is a carry that is generated, you ignore the carry. So, the result is 0 0 1 1 or 3. The same thing with minus 5 and minus 2. Let us look at subtraction in 2's complement representation. So, the subtraction in 2's complement is going to be negation followed by addition. We know that the negation in 2's complement is slightly more expensive. So, what we have to do is we have to first invert all the bits and then add 1 to it, that is how we get the 1's complement interpretation. We take the 2's complement interpretation of a number, right, this could be positive or negative. If I want to negate it, I flip all the bits and add 1, right. So, that is the way we do negation of 2's complement numbers. So, again I want to emphasize that negation does not mean it works only on negative numbers. Negation of any number in 2's complement form is you invert all the bits and add 1, that will give you the 2's complement representation of negative x if you start with x, and addition is performed as it was before, you ignore the carry. So, let us see the examples. So, I want to do 5 minus 2. Right? If I want to do 5 minus 2, what I really want is 0 1 0 1 minus plus 2 is 0 0 1 0. That is what I really want. What I instead do is I add negation of 2. So, negation of plus 2 is minus 2, minus 2's complement representation is 1 1 1 0. I take the 2's complement representation of the subtrahend. So, I take the 2's complement interpretation as it is for the subtrahend. For the minuend, I have converted that or I have negated it and I have added it together, and you ignore this bit 0 0 1 1. If you interpret that in 2's complement, that is number 3. So, let us look at this example. I want to subtract 2 from minus 5. So, minus 5 is the subtrahend. For minus 5, the 2's complement representation is 1 0 1 1, and plus 2's complement interpretation representation is 0 0 1 0. However, I want subtraction of plus 2. For subtraction of plus 2, I do it as addition of minus 2. So, this is addition of minus 2, which is 1 1 1 0 here. You add these and you ignore this, you get a result which is 1 0 0 1. Right? So, 1 0 0 1, I want you to go and convince yourself that this stands for negative 7. Right? So, it is easy to see because it is 1 0 0 1, it is starting with 1, so it is a negative number. Take 1 0 0 1, flip it, it is 0 1 1 0, add 1, it is 0 1 1 1, and that is 7. So, it is negative 7. Then look at these two, plus 5 minus minus 2. I want to subtract minus 2 from plus 5. So, plus 5 is 0 1 0 1 itself, minus 2 is actually 1 1 1 0, but I want the negation of 1 1 1 0, which means it is add the negation of 1 1 1 0, which is 0 0 1 0. You add these two together, that gives you 7, and similarly I wanted to go and work out minus 5 minus minus 2. So, when you do this, it is possible that there can be overflow. Some additions and subtractions can produce overflow that cannot be represented in the range that is given. So, for example, if I give you a n bit 2's complement number, if the result is greater than 2 power n minus 1, it cannot be represented using n bits. So, a 4 bit 2's complement representation cannot represent 8 and above. Right? So, it is possible that when you do your operation addition or subtraction, it may end up with an overflow, which means it is ending with a number which is not represented within the range, and many times it is useful for us to know that the resultant operation is a overflow. So, how do you detect that? If the carry into the MSB is not the same as carry out of the MSB, then overflow has occurred. This is true both for 1's complement and 2's complement numbers. Let us see examples. So, let us say I have 1 0 1 1 and I am adding 1 0 1 0 to it. So, 1 0 1 1 is minus 4, 1 0 1 0 is minus 5, adding minus 4 and minus 5 will give me minus 9. Minus 9 cannot be represented using 4 bits, right. That is the first thing you have to remember. Let us see how we can detect something like that. So, 1 0 1 1 added to 1 0 1 0. So, if I want to just add, I will add these two numbers, that gives me this 5 digit value. You take the 1, add it around, this is the end carry, and that gives you 0 1 1 0. So, if I directly interpret 0 1 1 0 in 1's complement form, it is positive 6, whereas minus 4 plus minus 5 is actually negative 9. The only thing that indicates that this is not correct is, let us look at the carry from this stage, right. So, the carry from adding 0 to 0 will give you 0 with a carry of 0, right. So, the incoming carry into the most significant bit stage is 0, the outgoing carry is 1 plus 1 is a 0, the carry out is a 1, right. So, the outgoing carry is not the same as the incoming carry, which means there is an overflow. Let us look at it for 2's complement numbers. In this case, let us see it for subtraction. So, 0 1 0 0 minus 1 0 0 1, 1 0 1 1. So, 0 1 0 0 is positive 4 and 1 0 1 1 is negative 5. I want to subtract negative 5 from positive 4. So, the result is actually 9. 4 minus minus 5 is 9. We know that it cannot be represented using 4 bits. Let us see how this is detected. 0 1 0 0 and negative of 1 0 1 1. Negative of 1 0 1 1 is plus addition, so subtraction of 1 0 1 1 is the same as addition of 0 1 0 1. You add these two now. Let us look at what happens here. So, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, the incoming carry is 1. However, the outgoing carry is 1 plus 0 plus 0, it is 1, the outgoing carry is 0. So, the incoming carry is 1 here, the outgoing carry is 0, which means there is an overflow in this. Even though you get a result 1001, if you interpret it directly, it will tell you -7, but if you looked at what is the incoming carry to the last stage and the outgoing carry out of the last stage, if these two are different, then there is a problem. Typically what computers do is, if something like that happens, the circuitry can detect this overflow and they will go and set a flag called the overflow flag. So, if you have done 8085 programming, 8086 or 8286 and so on, they would have taught you about this set of flags that are there in the processor. So, the addition of two numbers or subtraction of two numbers can result in the overflow flag being set, which means the result that you have is not correct. There is something that has happened to, because it is not in the range that is represented. Right. So, I want to end this lecture with this nice circuit for doing 2's complement addition or subtraction. So, if I want to do x, either add y or subtract y. Remember, x and y are both already 2's complement numbers, they could be positive or negative, I do not care. X is a 2's complement number and y is another 2's complement number. If I want to design a circuit that is either adder or subtractor, so I give a control from the outside, which is add bar slash sub. Add bar slash sub, the interpretation is, if add bar slash sub is 0, it means that you are adding. If add bar slash sub is 1, it means that you are subtracting. So, let us look at that. This circuit is beautiful. The reason why it is interesting is, this n bit adder is an unsigned adder. Taking an unsigned adder, if you want a 2's complement adder, all you have to do is, if I want to do x plus y, then put x here, put y here and set add bar slash sub to 0. So, if I put 0 here, what would happen is, you would have yn minus 1 XOR 0, that is yn minus 1 itself, y1 XOR 0 is y1, y0 XOR 0 is y0 and so on, right. So, we are giving the number x, we are giving the number y as it is, but with a carry in of 0. If you do that, then the sum that you get, right, is actually a 2's complement representation of x plus y. Right. In this case, you have to ignore the carry that is coming out. You look at Sn minus 1 to S0, that will be the 2's complement result of adding y to x. If I want to subtract y from x, so again x and y could both be positive or negative, I take x in its 2's, so x is already in its 2's complement representations. So, we put that x here, we put y here and we subtract. To subtract, we put sub equals 1, right, add bar slash sub equals 1. So, if you put 1 on each of the inputs of this XOR gate, so this output will be 1 XOR y0, which is y0 bar, this is 1 XOR y1, this is y1 bar, so on up to 1 XOR yn minus 1, which is yn minus 1 bar. This is equivalent to complementing the bit vector y. So, remember, if I want to do 2's complement subtraction, we do negation. So, we do negation of the input and add. To do the negation, this negation itself is 2 steps in 2's complement. You have to flip all the bits and add 1 to it. So, this part of the circuit is flipping all the bits, and remember, for add bar slash sub, if I put sub equals 1, the C0 will go as 1, this will take care of adding 1 to the results. So, essentially, if sub equals 1, we will have xn minus 1 to x0 added to yn minus 1 complement to y0 complement, and then another 1 will be added to it. So, that will be the result that you will get, and this number will again be a 2's complement number. So, the interpretation can be a direct 2's complement number. So, this is a very beautiful circuit, and this is how it is internally implemented in processors. So, this brings me to the end of module 49 for this week, and in the next module we will go and look at how to design a adder itself. So, in this picture, for instance, I said, let us assume that there is a n bit adder that can do unsigned additions. It is supposed to take two numbers x and y and maybe a carry bit that is coming in and give you a carry and a sum. So, I assume that this adder is a black box here. In the next video, I want to show how to design this black box. Once you know that black box, coming up with a 2's complement adder subtractor circuit is straightforward. So, subtraction is not completely different, all it required is a bit of XOR gates. If I want an n bit subtractor, all I have to do is put n more XOR gates, that is all. It is as simple as that for 2's complement. 1's complement is slightly more tricky. 2's complement is what is used in most computers. So, I will leave it here for next video. We will look at unsigned addition in the next video. Thank you, and I will see you in a little while.